Okay, so let's start. So last time we talked about the size distribution and charge distribution of the nucleus. So and so we mentioned the reason why we want to learn those. First is we want to learn the size and mass distribution because this is the better picture to think about the nucleus. They are not simple hard sphere. The second reason is those structures are important for us to understand the nuclear structure. Okay, and one of the important concept we use in nuclear engineering is the topic for today, is the bending energy. So now putting this bending energy in the quantum mechanics framework, and you can understand why we need the bending energies in two ways. So number one, we can use the bending energies and as kind of the potential of the interaction potential. Knowing the bending energy or knowing the interaction potential, we're able to derive nuclear structures based on quantum mechanics. Inversely, number two, you can also think about, if we know the nuclear structure, then can we derive the bending energy? So vice versa. And as maybe you have learned in 247, the bending energy is very important in nuclear energy. So let's talk a little bit of the bending energy today. Okay. So first of all, what is bending energy? So bending energy, so bending energy is B. You should use B to represent bending energy. It's a function of the mass number A and the atomic number Z, so A and Z. So for a particular nuclide with A and Z, then we can define the bending energy as essentially when you pull all the nucleons apart, how much energy does it take? So think about a simple example. It's a deuteron, deuteron is example, a neutron and a proton. Then the bending energy is the amount of energy that is needed to tear this deuteron apart, to separate the neutron and proton from banded together to infinitely far away. Okay, so that is the bending energy. Or the other way to think of bending energy is if you inverse process, if you have a neutron proton far away from each other, no interaction, and then when they get closer and closer, and when they band together, how much energy is released? So these two definitions are essentially the same thing. Okay, so this amount of energy is huge, and you may have learned how do we compute this bending energy is based on the math. Let me write down the math first. So this bending energy will be depends on how many number of protons we have. So we have Z number of protons, Z times the number of proton minus N numbers of neutron. Okay, so if we know A and Z, then we know N is just A minus Z. So we start from separated Z number of protons and N number of neutrons, and then we start put them together. So when we put them together, then we form a new nucleus. So the nucleus has a mass of M. So M, which is function of A and Z. Okay. Then minus, still need to take away the mass of the electrons. Okay. So this will be the total mass loss. So start from Z number of protons and number of neutrons, and when it fuse together to form a nucleus, then this is the mass loss. And using the famous equation from Einstein, so this mass loss times C squared will give us the energy. Okay. So this is the amount of energy released when you fuse neutrons and protons together into a nuclide. Okay, then we can rearrange this equation a little bit. We have minus Z times electrons here. Now electrons are very light, but when we think about a heavy nuclide, then like uranium, then we still have quite a few electrons here. And it might be better just put the electrons mass here as well. Then for minus Z times electrons, then we can merge this term between the proton and the electrons together. Then this is simply Z times mass of the hydrogen. So put the protons and the electron terms together. So that's the mass of hydrogen. This is approximately the same as the mass of proton, but it's more accurate to put as the mass of the hydrogen here. Then plus N times the mass of neutron minus the mass of this nucleus AZ. Okay, and then we times C squared. So this is the binding energy. And then, so the order of this binding energy, this nuclear binding energy, is typically in the order of 1 GeV range. Okay, how do we compute this? So we have C squared, and in front of the C squared, we have the difference in mass. So, and in the nuclear physics, we often use the unit of MeV or GeV instead of joules. So it might be easier to just write down C squared as a in terms of this unit. So C squared is equal to 931.50 MeV per unit mass. Okay, so then we can simply count. The mass and then time this 931.5 MeV. Okay, so it's close to 1 GeV. So the nuclear binding energy is typically in the order of GeV range. So this concept of binding energy itself is actually not new. In fact, we also have a similar concept in atomic physics. So in atomic physics, this binding energy is related to, instead of separating the nucleons from the nucleus, but separating electrons from the nucleus. Okay, so think of a hydrogen example. How much energy does it take to separate the electron? And that process is called ionization. Right? So, so in the atomic physics, this nuclear binding energy is analogous to the electronic, called the electronic binding energy. So, which is oftentimes the ionization. The ionization energy. Okay, how much energy does it take to free the electrons, to ionize the material? And usually this, we know, well, for water, that's how we define the separation between ionizing radiation and ionizing radiation. That's in the range of electron volts, right? And if you want to remove all the electrons from a nucleus, from an atom, then takes more than that. This is typically in the range of 10 to 100 keV. Okay, you can see the many order magnitude smaller than the nuclear binding energy. Okay. They are so small that so this binding energy equation, essentially what we just wrote here, can still be used to describe this electronic binding energy and ionization energy. But this energy is so small that the mass difference is also very small for us to detect. And that is why we do not really use this binding energy definition to compute this electronic binding energy. But in the case of nuclear physics, this amount of energy that gets released from nucleus is so large that we can have detectable differences in the mass. That's why oftentimes, if you want to know the binding energy, then we can easily just measure the mass of hydrogen, mass of neutron, and minus the mass of that nucleus. Then from there, we can compute the binding energy. Okay. But one thing that I want to point out that oftentimes maybe you hear or maybe still think of this way. So the reason we have nuclear energy is because of when we merge neutrons, protons together into a nucleus, then the mass is lost. So the mass is converted to the energy. Right? So I want to tell you, actually, that's not correct. So mass is never converted to energy. The mass and energy are equivalent to each other, but the reason we have this binding energy, or the energy gets released from when the nucleons merge together, is not because the mass itself is lost. So this energy ultimately comes from the strong nuclear interaction, still comes from the potential. Okay, just like in the examples I've shown you before, like this infinite square well potential. If you think about a finite square well potential, then when we put a particle in the potential well, then the amount of energy, the potential energy is going to decrease. And that much amount of energy is released from this fusion process. Okay. So coming back here, so this binding energy indeed comes from the interaction potential, which is the ultimate reason. And this potential energy is so large that this amount of energy released can cause a detectable difference in mass. Okay. Similarly, in fact, in the atomic physics, if you put a hydrogen, put a neutron and the electron together to form a hydrogen, okay. If the hydrogen falls into the ground state, we know the energy loss will be like 13.6 electron volts. It's a much, much smaller value. But in that case, the mass of the hydrogen plus the mass of the electron is also less than the mass of the hydrogen atom. So the above equation also applies to the electronic binding energy, except in this case, the mass of a hydrogen plus the mass of a neutron is very close or almost identical to the mass of the hydrogen atom, like this mass Az. So that is why we do not use this mass to compute the energy that is released, and we can directly measure the potential energy. And for nuclear physics, we do use this equation is because of this mass difference is much bigger than in the case of atomic physics. Okay, so this, in a way, this definition and this equation looks a little bit misleading because it makes us think, oh, the reason that we have such a large amount of nuclear energy is because of the mass gets lost and the mass gets converted to energy. And that is not the case. So the energy that gets released, it still comes from the potential energy. Okay. So otherwise, we can go this way. You know, we in atomic physics or even macroscopic objects, we have even bigger mass. How come we don't have an even larger energy? So we cannot easily just convert a mass to energy. Okay. So energy gets released still comes from this strong nuclear force. Okay. We'll come back next time. So using deuteron as an example, neutron-proton interaction, and there you can directly see the role of this interact potential, the strong interact potential on the nuclear structure and also on this bending energy. Okay, so for now, let's start from this terminology definition. This is the bending energy, and it's related to the mass loss during this fusion process. The other way around is the amount of energy that's needed to separate all the neutrons, the protons from the nucleus. Okay, so that is the bending energy. Then a much more common quantity we use is actually not the bending energy itself, but the bending energy per nucleon. Okay, so it's B over A. Okay. So when we have A number of nucleons, then how much energy, how much of the bending energy is assigned to each of them? Okay, so this is an interesting quantity because we can, if we can measure this B over A, bending energy per nucleon, then we can plot that for all the nuclei. Okay, so we can plot this B over A versus A. Okay, and for most of the nuclei, this energy, this B over A, is very close to the same. Okay, and this number is roughly 8.5 MeV. So let me put this, the unit of this axis is MeV. So this is 10, this is 5, this is 0. So for most of them, this B over A value is roughly 8.5 MeV. From light items to heavy items, light nucleus to heavy nucleus. And this is roughly understandable, right? Because of this amount of energy, it's related to the interaction, more precisely, the attractive interaction between the nucleus, between neutron and the proton, or between proton-proton, but not due to their Coulomb interactions, the nuclear interactions. Nuclear interactions still bind them together, right? Otherwise, you think about nucleus, we will have positive charged protons and neutral neutrons. How can they be bound together? There must be some force beyond the Coulomb interactions. If we only have Coulomb interactions, the protons will repel with each other and they will not band together. There must be some stronger force that is much stronger than the Coulomb interactions that can hold the protons and neutrons together. Okay, and this interaction, between the nucleus, between neutron-proton, proton-proton, neutron-proton, it should be the same, right? Should be close to each other. And this energy is roughly 8.5 MeV. Okay. And how do you know this is correct? And you can see with 8.5 by looking at the bending energy, for example, of just the interaction between neutron-proton, not the bending energy. Okay. So, and this 8.5 is roughly the interaction potential for neutron-proton. If you put neutron-protons next to each other, then how do you draw this potential well? Okay, and the depth of the potential well be roughly 8.5 MeV. So that agrees with the bending energy per nucleon. So this B over A is roughly 8.5. For most of the elements, they are very close to 8.5, and with a few exceptions. If you look at this curve, B over V versus A carefully, so there's it has a peak. So the peak, okay, it's roughly here. Let me draw the peak, and for heavier nucleus, beside this peak, this curve drops a little bit. Okay, And then for lighter nucleus, it drops a little bit as well, except for the very light ones. For the very light ones, like helium or lithium, then this curve has some oscillations. And the binding energy for deuteron, because of the lack of other nucleons, is the lowest. This is much lower. Okay. So, and helium, let's say this helium-4 here has a slightly higher binding energy, meaning it's more stable. And lithium-6 is here, has slightly lower binding energy. Okay. So besides those light elements, for most of the nuclei, this binding energy is roughly close to 8.5. Okay. So the higher the binding energy, what does it mean? So it means it takes more energies to separate that nuclide per nucleon. So that means the higher the binding energy, the more stable the nucleus is. If you look at this curve and our maximum binding energy, so that must be the most stable nucleus we have. Right? So what is the, let me put it here. So what is the most stable nucleus? It's iron, right? It's our iron, 56. So, and this is why, if you think about our Earth is basically a giant iron ball. And the center of the Earth is made of iron. That's why we have the North Pole and South Pole, the magnetism, right? So this is actually quite interesting observation. In fact, I can come back to explain a little bit more today if we have more time. So let me give you, before going that far, let me give you 2 examples. 2 examples on how to use this binding energy and how to understand this binding energy. So the first example will be, let's use this binding energy per nucleon to understand the fission. Okay. So for fission process, we start from, let's say, uranium. So let's put uranium here. So uranium, oops. So put uranium here. So uranium, the 235 or 238. Let's take 238 here. And then it has a slightly less binding energy compared to iron. So let's look at this fission process. So if you start with the element, this uranium, and A is 238, let's say roughly this is 240. Let's take 240 as an example. And if this nucleus disintegrates into 2 parts, disintegrates into 2 fragments. Okay. So, and to make the things easier, let's say these 2 segments, each of them has a mass of A/2. It's just half and half. And then we can estimate, based on this rough curve, how much energy is released from this process. Okay. So the initial state, we have the initial state, we have A, let's say is 240. Okay. And the B over A, if you look at B over A from this curve, like here, this point is slightly less than 8.5, and let's say 7.5 MeV. So the binding energy per nucleon for the uranium is close to 7.5. If I can look up the table, when I draw this curve, it's approximate, but you can look up this curve and you can see this B over A is close to 7.5 MeV. Okay. And after the fission process, after fission process, we get two fragments, and each of them is 120. 120 will be in the middle of this curve, like half of that. And then what is the binding energy per nucleon? B over A will be close to I, right? Not exactly, but close to the center of the curve, has a slightly higher binding energy. Let's say it's 8.5 MeV, close to this most probable value. Okay. Then we can compute using this binding energy per nucleon to see how much energy is released. This delta E, so the amount of energy that gets released, will be equal to 8.5 minus 7.5, right? So this is the decrease of binding energy per nucleon. Then times how many number of nucleons we have 240, right? So this delta E will be 240 MeV. Okay. So see, with a very simple estimation based on this binding energy, we're able to compute this fission energy, and it's actually very close to the real thing. Okay. So how about fusion? In fact, we can also use this to estimate the amount of energy that gets released in the fusion process. Okay. So let's consider like this DD fusion, like hydrogen 2 deuterium, deuterium fused into helium 4. Okay. How do we compute the amount of energy that get released from here? So look at this curve above. We need to know the binding energy of a deuteron. This is the initial state. Okay, this is initial state. So initial state, we have so we have the deuteron. So the B over A is equal to, well, on this curve, deuteron is an exception, has the lowest binding energy. So B over A is, if you look at this, it's close to 1. It's 1.1 MeV. Okay. And the final state of this fusion process, we get helium-4. So helium-4 is more stable. So the binding energy per nucleon is getting close to 8.5. The actual value is actually 7.5 MeV. Okay. Then by knowing this binding energy per nucleon, we can compute delta E, the amount of energy that gets released. So that'd be 7.1 minus 1.1 times how many nucleons we have here? 4. 4. So this would be 24 MeV. Okay. So that is also about right. So in this DD fusion process, and the energy that gets released is close to 24 MeV. Okay. So these two examples also tells us one very important use of this binding energy per nucleon is to compute the amount of energy that gets released in a nuclear reaction. Okay. So this is the binding energy, and in fact, we'll come back to this in a little bit. The beginning of development of nuclear model, in fact, focus on this curve. How do we explain this B over A curve? So without any nuclear structure, we think this B over A will be just a constant, right, 8.5. But as as nuclear physics follows the quantum mechanics, then indeed we have a nuclear structure. For example, why helium is more stable when we put only 4 nucleons together. Why is it so stable? And so the beginning of nuclear physics really focused on how do we explain this curve, B over A curve. So the full description of this curve, of course, relies on quantum mechanics. And, but there is a semi-empirical formula to describe this curve, and that is so-called the liquid drop model. Liquid drop model essentially is consider the nucleus as a drop of liquid, okay, with certain skin layer. So this goes back to what we talked about last time. And the nucleus itself has a uniform distribution near the center, more or less, and then close to the surface has a skin layer which has a lower density. Okay, and based on this picture, although it is not exact because of nucleus is not a continuous, nucleus has neutrons or protons in it. So, but on the other hand, if you imagine this nucleus as a drop of liquid, then we can come up with a formula to describe the shape of this curve. And that is very useful for nuclear engineering. Okay, we'll come back to that actually very soon. So, so that is the bending energy. So now coming back to this curve, B over A curve, and I think there are many things we can say about this curve. We talk about these two ends, right? So at the high A end, we have those unstable heavy nucleus that can be disintegrated, and we know this is the fission process, right? And I've already mentioned this is the fission process. Okay, and the energy is released during this process. If you go from the low A side, then we can also fuse nucleus through fusion process. But at the end of the day, we'll end up getting close to the top of this curve. And the very top of this curve is ion. So the most stable nucleus is indeed the ion. So this is actually has a huge consequence. So not I mentioned one of them. You know, the entire Earth is it's a gigantic iron ball, and that is because iron is the most stable nucleus. Okay. So if you think about further, the electronic structure is essentially determined by the nuclear structure. So like by electronic structure, so they are determined by how many electrons do we have. And how many electrons do we have inside atom is ultimately decided by how many number of protons do we have in the nucleus. So this curve, this binding energy per nucleon tells us that you know, what is the best way, the most efficient way to pack nucleons. So ion represents the optimum packing. So in ion, like we have 20, I think we have 26 protons, and 26 protons. Now we have 30 neutrons, 30 neutrons inside this ion nucleus. So that gives us the most stable nucleus. And then, so outside the nucleus, we must have only 26 electrons. So the chemical properties of the ion is determined by the number of protons, by the nuclear structure. And then we have 26 electrons inside this atom. Then the atoms, when the electrons start to fill in the atom, of course, they also follow quantum mechanics. We haven't done these calculations carefully yet, but from what we talked about before in the first section of this class, we know the behavior of the electron inside the ion follows quantum mechanics, right? So the energies are discretized, quantized, and there are many different levels. In fact, let me draw something here. So let's take this iron as example. So the interaction potential is 1 over R. Is V the function of R is inverse proportional to R, Coulomb interaction. So in this case, we need to pack 26 electrons inside this potential. Then the energy is quantized. We have multiple energy levels, and each of them represents one eigenstate of this entire potential. Now we can solve the sorting equation for this one potential, and we can find out analytical form for each of the state. Actually, that will be the task for next semester. But for now, without knowing the details, we can still draw this structure. Then electrons, when electrons are packed onto those structures, so, electrons cannot take any arbitrary energy. They can only take those discrete lines. Then we start to put electrons on those tracks, and those are called the orbitals. Okay, and this is not a one-dimensional potential, three-dimensional potential. So this third dimension, this angular distribution, allows us to pack more than one electrons onto each of the energy. So, and this gives rise to the so-called magic numbers in atomic physics. That's why we have the periodic table. So, and this 26, you want to put 26 electrons onto those states. And the chemical properties of the ion is really determined by only the outermost layer electrons. And for ion case, it's actually the chemical property is determined by the so-called d electron. So we'll explain more what is d electron later on. It's related to the angular momentum of the electron and SPD, electrons. So they represent different orbitals of electrons. So the chemical properties of the electrons is determined by this d electron. And the reason that this property is decided by the d electron because we only have 26 electrons inside the ion. And the reason for 26 electrons is because we have 26 protons inside the ion. Okay, so and why is this is important? Why is interesting? So d electron, they are roughly roughly here, because they are not the energy is not much, slightly higher than the ground state energy of the system. Okay. So the transitions, or the energy difference between these orbitals of the d electrons is actually in very low energy. The energy is so low that they are in a visible light range. So what is visible light? So visible light is in the order of so like 1.8 to 3.6 electrons. Right? So in other words, 350 to 700 nanometers. This is visible light. So 350 to 700 nanometer. In terms of energies, if you know the wavelengths, then we have the h bar times omega. So we know the wavelengths, we know the k, then omega is equal to c times k for photon. Then we have the omega times h bar, we get energy. So visible light, the energy is 1.8 to 3.6 electron volts. It's much smaller energy compared to nuclear energy, and falls right into the visible light range. Okay, so that is why you can see the color of the ion. You take iron to Fe2 plus. Okay, to Fe2 plus. What is the color? What is the color of the ion? It's red, right? It falls right into the visible light range. That's why maybe you have learned this in chemistry. We have a iron, and the color is red. So, and this is actually interesting because if you think about our human beings, so our blood is red, right? And the reason our blood is red is we do use iron to transport oxygen. So there are a couple of things related to this phenomena. And one of them is because of its d electron structure, iron has a quite active chemical reactivity. So iron can easily react with oxygen and carry the oxygen. We need oxygen in our life. So, and second is because of this d electron energy. So now we can see them with our eyes. So that's why our blood looks like red, because they contain iron. In fact, more specifically, the iron is contained in one protein called hemoglobin. So inside hemoglobin, we have this middle center, and they carry oxygen. That's why our blood is looks like red. Okay. So, in fact, if you think about most of the animals, living things on Earth, most of them have red blood, because most of them use iron to carry the oxygen. It's not surprising for two reasons. One reason is iron is the most stable nucleus. And second reason, because of this nucleus, it dictates the electronic structure, so that iron has the quite high reactivity with oxygen. So most living things use iron to carry oxygen. That's why for most living things, their blood is red. Okay, but there are indeed a few exceptions. Let's say if an animal use instead of using iron, use another metal close to the center of its peak, close to the center peak. Let's say copper. Uses copper to carry oxygen. Okay, what is the color of copper? Copper 2+. Maybe this goes back to high school chemistry. So copper is blue, right? So they also fall into the visible light range. So copper, but it's blue color. So if a living thing use copper to transport oxygen, then their blood must be blue. Okay? So indeed, there are a few animals which have a blue blood. So like spider, I think spider, snail, or I think octopus, they have a blue blood. So because they use copper to transfer oxygen. And but either way, whether it's iron or copper, they're all close to the top of this curve, the top of this binding energy curve. And oftentimes when we think about chemical reactivity, we don't think about its origin. It's usually due to the packing of the electrons inside the atom. But ultimately, the reason we have that number of electrons is really because of the number of the protons inside the nucleus. And the number of protons in the nucleus is determined by their stability, which is described by this curve, binding energy per nucleon. Okay, so so that's just another interesting story about this binding energy curve. So it's 9:46. I think we're just gonna stop here. So so next time we'll talk about a bit more about this binding energy and their features, and then that will lead us to the semi-empirical formula to describe this B overlay. Okay, so that is all for today. Thank you for your attention.